Challenge accepted, challenge accepted. The attitude is always challenge accepted. Challenge accepted, challenge accepted. The attitude is always challenge accepted.
Our next speaker comes from the United States.
And he has a typical American name, Dimitar Tcholakov.
Dimitar Tcholakov is actually from Russia, Bulgaria.
But before graduating school, Dimitar and his family went to Canada. Later, he joined the University of Waterloo, and being one of the best students there, he soon was spotted by some of the top-notch companies in the USA.
His journey to his dream job passes through giants like Scotiabank, BMO Capital Markets, Amazon, Microsoft, and Google. But today, we're about to see his biggest achievement so far. To speak at our conference here and today, make some noise for Dimitar Tcholakov!
Hello, folks. How you doing? Alrighty. So Peter saved the worst for last, so you can relax, chill, enjoy the buzz from the beer. We're going to have a quick journey through a bunch of interesting failure scenarios that have happened in the past. Some have been quite impactful. I guarantee you at least one of them has impacted you directly, and you don't even know it just yet. We're going to have a conversation about the future, how we can make it better. We're going to talk about how we can learn from the past mistakes and how much worse things are going to get as well. At least that's my theory behind that. So the agenda for the day is we're going to cover who am I and why are we here. We're going to talk about once upon a time when things were simple and things didn't really break all that much. We're going to talk about how things kept getting worse and worse and more complex, more intertwined. We're going to talk about how other things outside of just software impact system availability and reliability, and how much deeper you got to think about the stack versus not. We're going to talk about how best intentions are the reasons why all the major failures are happening these days, how the road to hell is paved for them. We're going to talk about the sins of our forefathers, and sometimes the actual fathers themselves. And of course, we're going to talk about how we can save the children, because at the end of the day, right, we care about the children and the next generation. And we're going to wrap it all up with a nice, fun example. I'm going to save that for later. It's a bit of a fun one. And of course, a Q&A. Hopefully, we have time for that. Awesome. So our two presenters kind of beat me to it in terms of who I am. So there's going to be a bit of an overlap in there. Please bear with me. But first and foremost, who am I? As they already mentioned, I was born in the city of Russia. My family moved to Toronto, Canada when I was a teenager. I graduated from University of Waterloo, ended up working in Scotiabank and Bank of Montreal there, mostly because those were the two places that had major big systems that I find very interesting to work on. Then I moved over to Seattle because actually it was kind of like a joke. We decided just to go there, try it out, see how it goes. 11 years later, it was still there. I worked in Amazon, taking care of the checkout backend and the actual order processing end-to-end. We're going to talk about the scale in a little bit. Then Microsoft, mostly dealing with the larger planning of all the data centers and capacity management there. And then Google, more or less doing the same thing. So, personally, I'm very happily married. I have two beautiful kids and a little puppy, although the second kid kind of scares me, by the way. The puppy is not as big anymore, not as little anymore, and neither is the whole family. So that's about it. Cool. Next one. Oh yeah, in my spare time, I do a lot of judo. If I'm not doing judo, I do more judo. And if I'm not doing more judo, I'm at the track trying to not get wrapped up around a tree. Alrighty, so why are we here? So we're here to talk about the complex world of reliability, availability, the many shapes and sizes of it, how to navigate it, how to make it better, and how to leave the world a better place. Alrighty. Chapter 1, Once upon a time. Once upon a time, things were easy. They were simple. Systems were easy. They worked in batches. There was no system-system interaction. In the good old days, problems were very isolated. They were very, small in scale. So when things broke, it was easy to know why, right? If a switch burns out, you can see it not lighting up. It was easy to fix. Banks still had paper ledgers. Everybody had backups to those systems because they weren't as reliable, so nobody assumed they would always work. So failures were kind of okay. But then as technology progressed, things became more and more complex. People's reliance on these systems became more and more complex. Information technology became more integrated in everybody's lives. You needed a computer to withdraw money from the bank, to book a plane ticket. Systems became larger. They still became more integrated with each other. And complexities rose as we moved along. And still, things were still easy to fix. They weren't that complex. They weren't as real-time. They were more batch-based. They were more BBS type of interaction, which made it, again, easy. But then again, they kept on changing quicker and quicker. Quick question. Who knows what Sabre is? Anybody? Ooh, some people knows what Sabre is. So Sabre is the very first massively distributed system that was ever used by a lot of people. Sabre was created by American Airlines back in the 60s, and it replaced literally dozens of books yay thick where agents would have to sift through to find a connecting flight from A to B. Sabre became so important to the industry that right now, literally every online ticketing service that you use to buy a plane ticket uses Sabre in the back end. It is so powerful for American Airlines, they can ground every single plane they have right now, and they will still keep making more than 50% of their money in revenue. So that was the first one. That was the very big one, massively distributed system. Of course, if it goes down, they still had the paper copies. Cool. But as complexity started becoming bigger, and we would rely more and more on these things, it gets a little bit scarier. For instance, we have a COBOL developer with 30 years of writing COBOL and nothing else, deciding to write their new .NET code. And they made all their variables global and not protected. So what could possibly go wrong? And I can tell you, it was a mess. It happened in one of the banks, and it took a while to clean up. But needless to say, people were able to see other people's accounts for a bit. We had another case of a fresh university grad that used the wrong encoding that messed up how addresses in Germany are displayed. And I can tell you the Germany post office was very unhappy about the lack of umlauts and the Strasse, the S in there. Then we had a fresh university grad that used the wrong data type, which led to an overflow and a very negative bank balance. And I can tell you this has happened multiple times in multiple banks. So it's not a one-off occurrence. We have another example of a fresh university grad, and yes, there is a pattern here, that fixed a piece of code that was written back in 1967. This was long before they were even born. And that fix caused a 2-day bank outage in one of the biggest banks in Canada. Thank goodness they actually had the paper ledgers because banks move very slowly. They operate very much the old way. That's why they keep making the same mistakes over and over again. But for 2 days, you walk into a branch because there was no computers available. You couldn't use an ATM machine. You go there and say, I need $100. And the bank had to trust you that you had $100 in your account. They would just write it up in the ledger. They would give you the money, and then you walk out. But then 2 days later, some poor soul in every branch across Canada had to go in and enter in all the data into the system. And in some cases, you had overdrawn your account. They had to go chase after you to get their money back. Again, it was fun. So outside of this one, the other things were fairly, again, simple, easy to catch. You have ways to prevent these things happening even right now. So, where to now? As you venture into the land of reliability and availability, the further out we go, the scarier it gets. And as we go in, the forest got darker and scarier. In other words, shit got real. All right, cool. In today's world, we rely on technology a lot, right? And everything failing now becomes an actual life or death situation in some cases. Here are some examples. Flight controls, air traffic control. If that goes down, planes crash, so people die. You have integrated hospitals. In some parts of the world, everything is digital. You get hit by a truck, you gotta get an X-ray. Before you get surgery, the surgeon has to see the X-ray to know what to cut, what not to cut. Well, if the system goes down, the surgeon can't see your X-ray. What happens? And that is something that has happened in the past, by the way, due to poorly configured hospital systems, but that's another story. Traffic systems. Every major city in the developed world uses a centrally controlled traffic system. If that goes down, accidents happen, people could die. So longer gone the days where we can say, if the system goes down, it's just somebody loses money. No, people can actually die now. So the onus is on us as developers to make sure this thing actually doesn't happen. And if that wasn't scary enough for you, we also have the ballistic rockets targeting coordinates for the land-based nuclear fleet in the US. And by the way, I gotta mention, this is a story I've heard that I haven't been able to confirm myself, but that whole thing runs on a spreadsheet with Excel macros. So next time you complain about Excel not working well, like nuclear holocaust is literally run by Excel. So appreciate it. And of course, if that wasn't scary enough, as we know, the most important thing in everybody's lives is sharing our blessed life with our friends and family. And if that goes down, I mean, come on, might as well just send the nukes, right? Cool. So now let's look into a couple of examples of recent failures and things that have broken up in a fun way. So imagine there's a loud cloud storage provider. They push out a new code change that improves their control plane, makes it much faster, better, more reliable. That's kind of a pun. And the nature of this change, because it's a control plane, impacts the whole region. In this case, it was all of North America. And the change goes out, causes a massive brownout due to a zero-day bug in one of the lower levels of the control stage. And let's just say that, I can't go into details, but let's say the hardware controllers were involved and smoke was present. Now, natural reaction is the new code is bad, roll it back right away, right? Push the new code in. Absolutely. Yeah, the problem is the deployment system was down because that system had dependency on that cloud storage because it was so reliable up until that point. So what do you do then? Well, you load the old version on a USB key, you literally drive for 2.5 hours to the nearest data center, you plug in the USB key, and you deploy the old version in the code from there, breaking all of the best security practices that you shouldn't be doing, ever. But that's what was necessary. So remember, circular dependencies are going to bite you in the butt every single time. And if you didn't get the meme, Jesus is wearing a cross, but he hasn't gone to the cross yet, because he's still alive. All right, cool. Another example. This one has an even more fun twist. A social media giant updates their DNS code. And to make sure it's actually safe, they deploy it only to their internal servers first. Sounds good, right? We don't impact customers that are using our services. Well, the server goes down. And every single machine, as a result, in the whole company is unreachable because that was the internal DNS. Well, the solution, get the USB key, drive 2.5 hours, plug it in, and get it done. Not quite. Why? Because the batch system you use to get into the data center runs off the same internal servers, so you can't even get inside the DC. And most of the data centers these days are fully automated. You don't have people inside of them. They usually stay outside. So what do? Solution 2.0, run to the closest hardware store, buy an angle grinder, and physically cut out the door so you can get in and plug in the USB key while making sure the police department doesn't shoot you for breaking and entering. Cool. What about a non-technical dependency, right? Because everything else, like, you know, it's in the stack. It's DNS servers, code, hardware of some sort. What about a non-technical dependency? So again, a global service provider launches there you go, we're back in. Has to launch a new product really, really fast. We have a conference coming in, it's really important, it's the keynote of the whole speaker conference. And then a crafty PM says, well, we got to launch it, but getting it through the regular DNS services is kind of a pain in the butt because it takes forever. We're just going to buy this little company over here and give them the, we got to get it done. And I can't get my corporate car right now, give them their personal one. 3 years later, the presentation was a success, everything was awesome, a lot of customers using this service now. 3 years later, the card expires. The DNS service company tries to renew the contract, but the payment bounces. They try and get in touch with the person that gave them the card, but that person no longer works in the company, so the email bounces. And they wait a day, a week, wait a month, and at some point in time they say, well, you don't pay us, we're not going to give you service. And they cut it off. Panic ensues globally. That whole URL doesn't exist anymore. So that was a fun one to fix. And it's only because somebody used their personal credit card. A non-technical dependency for your service that impacts it globally. Of course, it was a fun postmortem to go through, and there's a new policy that explicitly forbids using personal credit cards for any company usage. Alrighty, so as we go deeper and deeper into these conversations, I just want to try and think about, do you really know what is the full end-to-end stack of dependencies of anything you use? Pick up your phone, pick a single app in there, and try and imagine what is the end-to-end stack that relies, right? It's really difficult to map it. And by the way, this is not a software thing, this is the map of the Tokyo subway. I just thought it looks cool. But it could be, right? So, chapter 3. Out of nowhere, some hardware broke. Again, if we own the availability and reliability of our systems, of our services, if we expect people to rely with their lives on what we do, we got to care about the full stack, including the hardware. So, this is probably known for some of you, but I just want to make sure we cover it, right? So we've got the OG bug, the original gangster of a bug, and why we call a bug an actual bug. Back in 1946, they were still building computers. Technology was still very mechanical in the computers itself. The relays would physically open and close. And they had lights and it was warm, so that light and warmth attracted a lot of moths. And one day, for a while, the machine just wasn't working right. And the engineers went in, looked around, figured out that in one of the relays, there was a moth that literally got killed, and it was preventing the relay from closing, preventing it from actually making contact, giving you the right, the math. They took out the moth, and because they're still learning about this technology, they put in a book, in a ledger, that says, yeah, we had a bug in the system that caused a system failure. So that's why we call it bugs, because of an actual physical bug. So, what are some hardware failures that cause issues? A data center in Paris was lost due to a power substation fire caused by protests. So now we got to worry about geopolitical events. We had a few years prior to that, we as like all of North America, lost connectivity to Southeast Asia because there was a luxury condo being built in Hong Kong, and they cut through the whole fiber network backbone. Restoring that was a pain. It took forever. And yes, you had backups through satellites, but that connection is way slower, so that didn't work so well. But it can get worse. How much worse? Keep that picture in mind, it's going to come in place in a second. How about natural disasters? So the state of Virginia is home to the largest concentration of data center capacity in the world. We can talk in the Q&A why that is the case, but it is the case. Right now, there are 4.4 million square meters of capacity already available, like data center capacity present, with 5 million more coming live the next couple of years. That's like over 9 million square meters of actual data center space. The picture you see is the center of Sofia. The red box is 9 million square meters. It is that big. Imagine all of that just data center space, nothing else, racks. Now, the problem is that all of that disproportional capacity is located nearish to the Atlantic coast. And with global change, global warming, we have a lot more severe storms. So a few years ago, a hurricane rolled in, flooded a whole bunch of data centers, which went down. Traffic got routed to other places, but they weren't enough to handle the traffic, and you had a rolling brownout across all of North America. So these days, the weather forecast is part of the daily scrum, because you got to get ready for it. Now, if we didn't have to only worry about, if natural disaster was the worst thing, we also got to worry about sharks. That is a real picture. So this was in the early 2000s. Google engineers because Google has their own fiber network present throughout, in quite a few places. They were promoting, they were doing a regular service, a regular undersea survey, and they noticed there was a shark that was just biting at the cable, really chomping at it. You can actually go on YouTube, you can search for shark biting fiber optic cable, you'll find plenty of them, because this was not an isolated incident. It happens all the time. It is one of the reasons why in Vietnam right now, they still don't have high-speed internet, because they weren't able to solve the shark problem. And yeah, the solution, Google had to engineer a new shark-proof fiber optic cable that used a proprietary mix of Kevlar and steel and so on. So yeah, you got to worry about sharks. And I personally really hope that the Meg is not a real thing, because then you can forget about posting pictures online. Cool. So, next chapter. Good intentions. And this is the gist of what we're going to talk about. The overwhelming majority of outages are caused by good people trying to do good work for good reasons. But because the world we live in is becoming so complex, things end up blowing up because we don't know the full thing. Again, remember my example with do you know how your app works end to end? Here's an example. So a crafty developer found a new object that was attached to an entity that is present in a larger document that they have to use for their order processing. It's in production, it works, it did exactly what they wanted to, it speeds up their time to market by months. Amazing, right? Who wouldn't use it? Well, 2 weeks later, after they launch in production, this whole thing just disappears, and the use case breaks, the whole business line goes down the drain. Why? But where did the data go? What happened with it? Well, there's a clue in the name. If you look at the object, near the end of it, there's this little warning. Somebody just didn't do a good enough job of reading it, or maybe assume that, oh, that's a leftover because it's running in production and it works just fine. So again, good intentions. There's another example of unintended consequences, right? When you look at the larger data center management, you have to constantly move things around. You have to constantly optimize usage in different pools and make sure they're running as optimally as possible. If you have a pool that is running too cold, but the one that is running too hot, you want to move things around, whether moving the demand or the capacity itself. And specifically when you do that with storage machines, there's extra complexity you got to worry about, which is data availability. If you pick the right machine to move in the right sequence, in the right place, you can end up with half of your bytes in a specific cluster sitting in a single rack. Now, what happens if that single rack goes out for maintenance? Best case. Worst case actually blows up. Well, you end up with data loss. Because somebody did the right thing of balancing the machines as quickly as possible without knowing about this particular rack going in maintenance fairly soon. Right? So, unintended consequences by doing good things only. So, this is really my main idea. We're all screwed. Because the majority of most of the major outages we're going to experience in our lives as developers have already been put in place. There's nothing you can do about it outside of triggering them. There's a lot of zero-day bugs that we haven't caught. There's a lot of very complex interactions that have already happened that you don't know about that are there. So you will suffer because of decisions made by others years ago. And similarly, you will make others after you suffer because of decisions you're making today. In the next chapter, we're going to talk about how to minimize that pain as much as possible. Let me give you a more detailed example of what happens when you really want to do a good thing, and then it bites you in the butt years later. So this is a general, distributed architecture. Think of a application gateway. Cloud service where you can deploy your application, you can put it in. You have a fairly complex model behind the scenes where you have the application, different instances, user groups. We're going to go into that in a second. And the important thing is that everything in this system is an application, including the application itself, the application gateway. And as I mentioned, the model is fairly complex. This is not even scratching the surface of the actual reality. And of course, you want to be very distributed. You want to have different slices to minimize any blast radius. So you have slice 1, which is used for staging. Slice 2 is the actual, other prod cluster copies. And because nobody likes to use staging for actual production use cases, but you got a test in there, it's kind of like a pseudo-test environment, right? But it's in production. But because it's in production, it's used as a backup for the actual proper cluster. Data is synced up between the databases, between the slice 1 and slice 2. Now, there was a SVP demo that had to happen very, very quickly for a new version of that application gateway, which was supposed to be super cool. And in the dev environment, we had the proper, the new version of the application, which was copied over to the staging environment because we want to show the SVP that it works in production with real data, right? Makes perfect sense. And because we don't want to override the existing proper application, the proper app gateway, we created a new one. We just made a copy of the one in dev. We pasted it in staging, and of course we changed the name to, app gateways SVP demo. Once the demo was over, success, everybody cheers, everybody's happy, the object was deleted. Now, this is a very touchy system, and deleting objects is a scary thing. So the policy at the time was that you'd never physically delete an object. You only label it as deleted, because space is cheap, and nobody cared about it, right? So you have this name, this thing called an app ID, app gateway, SVP demo with an app ID of GUID1 that has a status of deleted. Cool. 6 years later, company policy changes. And now we say, well, we have a ton of these deleted objects that are just polluting the system, and they're causing issues for. So how about we just start deleting them permanently if they haven't been used in less than 3 months or a year? Doesn't really matter. It's less than 6 years, let's put it that way. So you have a little query that you put in place, and you start executing, and it says, hey, so for every application that has a deleted status of true, and go and purge all the objects associated to that application. And of course, afterwards, delete the actual app itself as well. You run the query, and of course, what do you see? Well, you find the app SVP demo, which is perfect, like go delete everything. Yeah, but you do the search based on app ID. And what was the actual application gateway GUID ID as well? It's the same one. Because when people copy the object, they never change the GUID. They never changed the GUID because the GUID was supposed to be unique. Nobody verified the GUID was unique when you copied it over. There were no checks and balances because it's actually quite expensive to check one ID across a very distributed system that is global. And people assume that the GUID is always unique, a globally unique ID. So the purge logic went in, killed the SVP demo copy, yay, go team, and then it killed in the actual proper gateway application. It deleted all the users, all the instances, all the private keys, all the public keys, everything. Gone. That was a fun few hours of restoring backups and trying to figure out what's happening. By that time, this application gateway is used by millions of people worldwide, and some data could not be recovered. So those are very uncomfortable calls being made to customers. So I guess more of the story is, don't copy test data into prod. So yeah, the whole thing just went down. Cool. So now that we know how horrible the world is, how do we make the world a better place for the folks that come after us, right? Doesn't have to be our children, but certainly the next generation of developers. So think about the children, okay? You got to think of a few things. You got to prevent outages from happening. You got to be able to detect outages when they happen. You got to be able to mitigate them really, really quickly. And you have to prioritize that work. And then, of course, you got to resolve any issues and rinse and repeat over and over. This is a continuous improvement process. It's not a one and done. So let's go over through each one very quickly. Prevent. We are, as developers, are not paid, at least in my team anyways, we're not paid to cover the happy case. That is the easy part. We're paid to cover the edge cases, the failures that can happen without us knowing about them. So you got to think of these failure modes while you're doing the design, not once you're done coding and you're doing testing. That's too late. That's expensive at that point in time. Because it's expensive, you're more likely to be told, how likely is that to happen? We'll fix it later. I've seen to-do items in code written back in the 60s, which was not touched 40 years later. So don't do that. Think about reliability at all levels. You got to think about the code in IDE. This is where you have the proper style guides in your IDE. You have proper unit tests. That's how you protect against global variables written by a COBOL engineer. You have to think about the system integrations, how one system talks to the other. So these are your integration tests, having your proper staging environment, having a good version of what happens in production. Not a perfect thing, but you got to think about it. You got to get it done as quickly as possible, as much as possible. You got to think about the larger ecosystem. What are your continuous deployments looking like? Do you have stage rollouts? Do you have a way of minimizing the blast radius of any potential thing going someplace else? And a pro tip to some of you, because I've had this conversation more than one time, so I know it happens all the time. Having a single global fleet with more machines to which you deploy one at a time is not the same as having a fully segregated slices that are completely independent of each other. You have different failure modes in each one, but they're importantly, you have to stick to the second one, sorry. So, do you have any data center versus zone versus region versus global push? Which one is safer? How do you balance between these two? And do you know how your system behaves when something goes down versus if something acts weird? If I rely on data accuracy, can I trust that data comes my way if it only comes my way? If the data is here all the time, then the system works, but does it work correctly? All of a sudden, you got to worry about that as well. You can't just believe that it's going to happen. And of course, all of that, you got to balance against your budget, because reliability is expensive. It is very, very expensive. Going from 3 nines to 4 nines is an exponentially more expensive endeavor. Going from 4 nines to 5, even more so. It's orders of magnitude more expensive. You need more locations, you need better distribution across the world. It is not cheap. So you got to balance it out. You got to know what your business case is. Cool. Detect. You got to have the right dashboards before you launch anything in production. You have to know exactly what constitutes health in your world. And there's some best practices I want to share. Number one, your dashboard has to be easy enough to comprehend. If you just had the best night of your life, you're drunk you're super, super drunk, and you get paged at 3 o'clock in the morning, you gotta be able to say, I know what's broken, and it's right here, because it's visible. That is the bar you want to have for yourself for your dashboards. If it requires any more cognitive skill than that, it's too complex. You got to figure out what are the right things to measure. What are the upper and lower bounds of acceptable values for each of these things? What are your SLOs, SLAs, et cetera, et cetera? You got to be able to figure out what is the right tooling you need to have to pick the right data. And of course, you got to have different layers so you can dig into different places. And again, this is a design time activity. You can't think about your key metrics once you write your code. Refactoring those in is expensive. It takes a while. And I also guarantee you're not going to think about the right things. So you have to know, during design time, what are my metrics for success? How do I know my system runs right and runs well? Granularity matters. Too fine-grained, you can't see the forest for the trees. It'll be too noisy. too coarse-grained, and you end up not being able to process a single order in Canada because you bundled the Canadian orders with the US orders, and the ratio is 1 to 50. So you had no idea that something was broken in Canada. This is back from my Amazon days. And of course, you got to define your SLO and SLAs and balance them with your ability to support them. You may want to have a 5-9 availability, but do you have the right support structure in place? Do you have a globally distributed team that can handle 24/7 scenario? Yes or no? Most cases, it's a no. I guarantee you that most places that say they have a 4 or 5-9 availability actually don't. And you know about it. I mean, you have it until you don't. Mitigate. Do you have a launch and rollback plan when you push new changes out? Can you undo changes very quickly? Do you even know what the recent changes were? Do you have the ability to understand that information? How fast can you push out new changes once you know something is broken? Do you have the angle grinder ready in your car, or do you have to buy a new one? That stuff matters. Then, do you have the right people available to help you solve the problem? Can you get in touch with the right people? Do you even know who they are, depending on the specific thing that breaks? These are, again, think of the big systems. These are complex ways. You have to have the right structure. You have to have the right process in place. And of course, you got to prioritize them. It is very easy to always chase after the new shiny business initiative and to leave technical debt behind. We had a couple of speakers that talk about this already. It is difficult to prioritize, but you have to do it. You have to bring the right engineering excellence best practices, and you have to build the right culture of improvement in there. So, you gotta find this balance between reliability, availability, and business goals. This is where you as engineers need to hold your management accountable, and management needs to empower you to hold them accountable. If that's not happening, go get a new manager. Cool. Do not normalize deviancy. It's the broken window syndrome. You say, this is small, I'm gonna fix it later. Later never comes. Have a high standard of what works, what doesn't, and what would be a massive issue later versus now. And of course, resolve it. This one's easy. Just fix the damn thing. Like, if you know something is broken and it's caused an issue, you're gonna fix it. That's an easy one. Rinse and repeat. That's a hard one. You need repeatable processes. You need to build a culture of engineering excellence in the team. So people have to lose sleep over things that are breaking. Cool. Now, things broke. The patient is dead. What do we do now? Well, you have two ways of approaching things. You can learn from your mistakes and evolve and do better, or you can take the theological approach and pray and hope for the best. Personally, I prefer my operational life to be very boring. I don't like excitement in my life. So let's focus on that for a bit. So all the major tech companies have some sort of a post-mortem process that basically, it's a very formalized process for a reason. There are very mandatory steps for a reason, because we want to make it repeatable. We want to make sure that it happens every time something breaks. And it's not half-assed one day versus the other, right? Google has a blameless postmortem, that's the name of it. Amazon has a correction of error, a COE. Microsoft has a post-incident report, PIR. And these things are more or less the same. There's some variations, but the process is kind of like more or less the same. First and foremost, what's the timeline? You gotta know what happened. You gotta understand what happened, what were the key events, when did the incident start, how long did it take us to detect the incident? Did we try and fix it? How long did it take us to fix it? How much time did it take us to actually resolve it? That tells us our ability to mitigate, tells us our ability to understand the problem, and so on and so on. And you want to drive that down as much as possible. What actually happened? Who did what? Those are key things. Then you got to embrace your 3-year-old, your internal 3-year-old. You got to keep asking why. Something broke. Why? I don't have money. Why? Because I spend it. Why? Because I like drinking. Why? Because I had a rough childhood. Maybe, maybe not. Why? And so on and so on. You keep on going until you get to the actual end where there's no more whys to be asked. That's going to lead you down to a lot of different paths. And each of these paths must have at least one or more root causes. The root cause, well, you also need to, before you even get there, is like, well, you got to understand where you got lucky, right? Did you get lucky with something going very much your way and having a less of an impact? So did you pick a four-leaf clover, or did you have bad luck and you had a no-leaf clover in there, right? Usually, we over-bias on being unlucky, and we say, this would never happen again, and we simply under-bias on being lucky, where things could have been much worse, but we didn't know about it because we got lucky. So that's important. And then, that drives the urgency of fixing things. Going down to the root causes, as I mentioned, every Y path needs a root cause. That's how you guarantee that you're fixing things holistically. You got to look at what each cause was, why, what, how, when, etc., etc. And of course, there's many different ways you can do that analysis. I'm not going to go through each one of them because I'm out of time, actually. So we're going to hurry it up a little bit. But the idea is that every root cause then has an action item. That is how you actually improve your system, you make things better, and you move along. Every root cause has at least one or more action items, no exceptions. Each EA must have an owner and an ETA, otherwise it's just a best wish. And each EA has to have an action, like ideally we want to link it to something that is in the system, and we need to have a process, a mechanism of reminding us what we got to go fix, because otherwise it's going to break. And so usually they go into categories of prevent, detect, mitigate, same as what we do before, right? Fix and so on. So once again, I can't stress this enough. Do not normalize deviancy. It is the reason why bad things happen. It is the reason why people get used to things being done the wrong way, and then you continue doing it the wrong way until they blow up in your face and you got to pay the price. I keep telling every new hire that I have in the team that for the first 6 months of their lives in the company, any place you go, you have a superpower. That superpower is not knowing a thing. And because you don't know anything, you're going to have a ton of questions. And some things are not going to make any sense because you just lack the context. Other things are not going to make any sense because it is actually stupid. So write them all down. After 6 months, you're going to get used to the stupid things, guaranteed. And you won't pay attention to them anymore. So write them down, have a chat with your team after 6 months and say, hey, this still makes no sense. It's still stupid. Why are we doing it? Don't get used to it. And please, for the sake of our children, don't try and get better, right? Like, take this to heart, try and make the systems as resilient as possible, and make it easier at least to recover from those outages for the next generation. Cool. And I said a fun wrap up. Let's say you've done everything perfect, and your system is the most reliable thing in the world. You have N9's availability, where 9 is greater than 100. You can still get to experience some excitement from an operational point of view. I'll give you one example. This is a few years ago. Amazon had just launched in India a few months prior to this incident. Things were going smoothly, everything was great. And then all of a sudden, traffic drops down to 0, just wham, like a rock. Alarms go off, people freak out. In my world, we had something like 250 first-line dependencies, 750 second-line dependencies. Ceph0, Ceph calls get spun up, everybody's there. About 150 people on the call trying to figure out what the hell's going on. And everything is okay. All the dashboards are fine. Everything is okay, just traffic is down to 0. In somewhat of a desperation, because we thought maybe another cable got cut, we called one of the local network providers to see what's going on their end. And that person was very grumpy because we interrupted him watching the Cricket World Cup, which was happening at the time, and we had India and Pakistan going for the finals. So literally the whole country was watching the game, and nobody was shopping. So there was nothing broken, but alarms went off, and people freaked out. So since then on, major sporting events are now part of daily Scrum as well. Alrighty, cool. So I don't know if you have more time for Q&A, but I don't know. Do we? Oh, yeah, we have time for Q&A. Any questions? Nobody wants to know why Virginia has so many data centers? Oh, come on. That was an easy one. No? Okay, fine. I'm not going to tell you. Quite a few reasons. Number one, tax incentives. It is really, really cheap to build a data center in Virginia. Number two is there's a lot of military bases, and the birthplace of the internet was in Virginia, and as such, there's a lot of good fiber optic infrastructure in there. all of the transatlantic cables, at least most of them, land in Virginia. So it's a very convenient place for that. But mostly because of tax incentives. No, they're sharks. It's just now we have the right cables in place. Awesome. Anybody else? All right, cool. Well, in that case, I'll wrap it up, and I'll be at the speaker's corner if anybody wants to chat some more. Thank you so much, folks. Everyone.
Thank you. It was really interesting. And if you have any questions, you can find him in the beer's corner.